All right, let's dive into some of these other review problems just a piece at a time. So let's take the next couple pieces here. That first section under part 4 in there was just other average or other rate of change type things. Well, if I give you this particular problem, this is a great context problem that has come up in the past that I like. It's CVS Pharmacy. There's sales, and if you want to talk about average rate of change over a period of time, that's always a good explanation of how things are going. You know, average rate of change over a period of years. On average, this is what we're seeing for rate of change. And the way you get that in part A down below is you don't do any derivatives for average rate of change. You just do the value of the sales at 2008, which is 8. You input 8, t equals 8. Sales at 2005, t equals 5. And then take those two values and then divide it by the number of years, 8 minus 5, 3 years. So it's change in y over change in x. Or you can, there's a couple other ways to describe it, but down below you'll see how that takes place. The result for the two sales values. Now what I did is I just put these in a calculator. I got the value at 2008, got the value 2005, subtracted, and got 56. And of course 8 minus 5 is 3. So on average, I'm getting 18.6871. Now, the most important part, what does this represent? And it's always output, billions of dollars in sales, per 1 unit of input. So this is a year, 1 year. The next piece is, it says find the instantaneous rate of change. That's where derivative calculus comes in. A derivative at a moment, slope of the tangent line, those are the synonyms for that. The s prime of 5 and s prime of 8, if I actually just give you the values right now, and I'll show you how I get them next, they are 10.5 and 14.95 respectively, billions of dollars per year. So they are the same unit as the average rate of change, but they're at a specific moment in time. And notice the average is higher than the two rates at the end points. That means somewhere in between those years, we had some pretty high rates of change that would have had to contribute to this average of 18.6. So here's the derivatives. So if I take the derivative of this function, I've got it here. You multiply the exponent out front and then you subtract 1 from it. And this is the result. If you put 8 in there, or 5 in this case, that's what I get, 10.5 going out. Literally put them in and square it, so you have to be careful. I'd try it on your calculator, make sure you can in a pinch, because you will have one like this on the final. And 8 as well, put that in, you should get 14.95. That just gives you something to check against if you want to know how to do that. Know how to take the derivative, know how to put a value in. And then from there, it's to compare those with what you got for the average rate of change. Well, if the rate of change of increase between these years is higher than the average rate of change, if we have the two endpoints and then something in between so if I give you a sense of, I might draw something a little extra on this picture here. I got this average rate of change that is a secant line slope, and then the instantaneous rates of change around it that are different. Well, the two on the end are lower than the average in between. That means there must have been a pretty high rate of increase at some point in between the years 2005 and 2008, so that the average would be more than what you see at the end points. All right, moving on. There's another problem, number 22. So we have monthly demand, and this is where if you have demand and you have a cost function, how can you get the profit? Well, profit you have to know is revenue minus cost. Just have that general idea in your mind. And revenue is price times the number of units. So you'll see that right here, price times number of units, or X. So X is the number of units. That's your revenue. And we've talked about in other contexts, minus the cost, which you see in parentheses on the right. That's your profit function. We'll distribute and simplify. You always want to get this down to as simple a term as possible if you're going to have to take a derivative, which we will, because B says find the rate of change of profit when the monthly sales are 700 units. That's a specific point. It means we're going to take a derivative and put this value 700 in there. So first let's get P down to something a little more manageable. It's not the derivative, it's just simplifying. So it's just profit. The derivative, so here's the function itself again. I just copied it over. The derivative then would be here. Okay, so I multiply 2 times that 0.0. I put it back in order. When I did profit, I didn't put the highest power out front. I rearranged it for the derivative, but this is the end result, and I'm sure you can follow that just fine. But putting 700 in there, we would get an average or an actual instantaneous rate of change for 700 units of production. And then, of course, you want to tell me what it is. So output is in dollars, and input, the X, is units. So that's $1,437.60 per unit. That unit piece is so important. But that's two more rate of change functions in some kind of context, something similar to what we did in class. All right, I'll bring more later.